how a basic web app works. So in this part, we will talk about how a basic web app works. So let's start by saying like designing a system that supports millions of users is challenging, and it's a journey that requires continuous refinement and endless improvement. So in this section, we will build a system that supports a single user or very small users and gradually scale up to serve millions of users. Okay, so we will start by designing a basic web app, and then we will see how we can improve our design to support more number of users or ultimately support millions of users. So let's see. So as it is said, like a journey of 1,000 miles begins with a single step, and building a complex system is no different too. To start with something simple, everything is running on a single server. So we can start by assuming our website is running on a single server. So let's see this diagram and see how a simple website with a single server works, right? So in this, we can say we have a user which is either using a laptop or a mobile to access the website. So user access the website using the domain names such as some API dummy.com or so. And then this request goes to domain name system or DNS, which is a paid service that is provided by third party and are not hosted on the original website server. And this DNS in return us an IP address. And once the IP address is obtained, hypertext transfer protocol requests are sent directly to the web server using the IP that we got, and the web server returns pages like HTML pages or JSON responses for rendering the data on the UI. Okay, so in this way, how a basic website works, and we can say that traffic to a website comes from two sources. One is a web application or a mobile application. Here, by web application, we mean is a combination of server-side languages like Java, Python, or so to handle business logic, storage, and etc. And client-side languages like HTML, JavaScript, and so. And on the mobile application side, we use HTTP protocol is a communication protocol between the mobile app and the web server. And JSON is commonly used in APIs as a response format to transfer data due to its simplicity. And so basically, we use generally JSON to basically communicate between a mobile app and the web server. So in a way, that is pretty much on how a basic website works. So in the coming videos, we will try to add up more things in it, or basically to scale it for millions of users. Database. In this part, we will talk about database. So with the growth of user base, having a single server to handle the request and save the data is not enough. We need multiple servers, one for handling the mobile web traffic and other is to handle the data part. And for that, we will use database. And basically separating web and mobile traffic, that is web tier, and database, that is the data tier servers, allows them to be scaled independently. So yeah, so that's why we should divide them. So if we see in this diagram, now we have introduced a database which we will use to write the data and read the data. So we have introduced a data tier here to handle all the requests for data and basically to write in database and read from database. So now what is database? So database is a collection of organized and structured data that is stored and accessible electronically. And for doing this, we use a database management system, which is used to create, manage, and manipulate the data in the database. The purpose of the database is to store data and retrieve data effectively and accurately while ensuring the integrity and the security of data also. So database are used in wide range of applications, including e-commerce, healthcare, manufacturing, and education. And they are also used in everyday applications such as social media, online shopping, and search engines. Now, there are several types of databases. The first one is relational database. So relational database are the most common type of database, and they store the data in form of tables and rows and columns. And they use a structured query language called SQL to manipulate the data. They are also called as RDBMS or relationship database management systems or SQL database too. And the most popular ones are MySQL DB, Oracle database, PostgreSQL, and these database represents data in form of tables and rows. And we can also perform join operations using SQL across different database tables, so to get the data from different tables also. The other variety of database is a non-relational database. So these databases are generally designed to handle high volume of unstructured or semi-structured data, such as social media post or sensor data. They do not use SQL and are often used in big data applications. And popular NoSQL databases are CouchDB, Neo4j, Cassandra, HBase, Amazon's DynamoDB, and so on. And these databases are further grouped into four categories. One is the key value store kind of database. Then there's a graph store kind of database. Then there's a column store, and then there's a document store. And join operations are generally not supported on these non-relational databases. Although some versions of them are there, but they're not by default supported in these databases. And they use some kind of appers or things to basically handle that. Like in MongoDB, we use aggregators to do the join, but no, they are not that much performant on that side. Okay, so and for most developers, relational databases are the best option because they have been around for over 40 years, and historically they have worked well too. However, if the relational databases are not suitable for your specific use case, it is critical to explore beyond relational database. So non-relational database can also be a right choice for you if your application requires super low latency, if your data are unstructured, and you do not need or have any relational data. If you want to serialize and deserialize your data, like you're using JSON, XML, and YML a lot, and you want to serialize and deserialize them, and you need a massive amount of data, then going with the non-relational or NoSQL database makes more sense. Now let's suppose load on our database increases, and like we are getting requests for more number of users, and or basically we want to scale our system to support more users. So we can scale, so we have to scale our database too, and database can be scaled in two ways. One is vertical scaling and other is horizontal scaling. Okay, so we can talk about vertical scaling first. So vertical scaling referred as scale up, which means the process of adding more CPU power to our servers. Like initially we have a small CPU, then we added a more powerful CPU, and if the scale increased further, then we will add a more powerful, like a most powerful CPU or more powerful than before. Whereas horizontal scaling, it means to allow scale by adding more servers into the pool of resources. So like in parallel, we start adding more servers. The server size is still the same, but we have added more servers to achieve that scale. So this is called as horizontal scaling. So when the traffic is low, vertical scaling is a great option. And the simplicity of a vertical scaling is a main advantage why it is a great option. But unfortunately, it comes with serious limitations, and that are vertical scaling has a hard limit. It is impossible to add unlimited CPUs and memory to a single server. Like there's a limit to how much hardware or infra we can add to a particular server. Like we cannot go beyond the most powerful CPU or the most powerful processor or storage or the highest space we have. There's a limitation to the amount a system can be vertically scaled, and that is also very costly too. Like adding so much powerful or so much huge storage is a quite costly effort too, and there's a limitation to it. And the second limitation for vertical scaling is it does not have a failover or and redundancy. Like if one server goes down, then the website goes down with it completely. Like since all the data is residing in a single node, right? So there is a single point of failure. So if that node goes down, then everything will go down. Like there's no backup or no replica or no shard to support this thing. On the other hand, horizontal scaling is more desirable for large scale application due to limitations of the vertical scales. Like we don't have single point of failure. We have multiple nodes which are acting here to give us and to read and write data. So there's no single point of failure, and like there's no we can add a number of nodes, and like since all nodes are using a limited hardware also, so there's no limit. So in that sense, going with the horizontal scaling is better when we want to scale database to more number of users. So yeah, that is pretty much on the database part. So in this part, we will talk about load balancer. So let's suppose if many users access the web server simultaneously and it reaches a web server load limit, then users will generally experience slower response or fail to connect the server because all the load is going to a single server or so. So basically, we need a load balancer here, and it is a best technique to address this problem. So let's see what is a load balancer. So load balancer is a networking device or a software that distributes network traffic across multiple servers in a server cluster or data center. Its primary purpose is to ensure that no single server is overloaded with the traffic, that all servers are used efficiently, and it ensures that all servers are used efficiently. Load balancers works by distributing incoming traffic to a group of servers based on the pre-configured rules, and these rules can be based on several factors including server availability, server health, server capacity, and type of traffic being served. Okay. And basically, there are two main types of load balancers that generally we use. One is the hardware load balancer, and other is the software load balancer. Hardware ones are the physical devices that are installed in a data center and that are dedicated to balancing network traffic. Software ones are applications that run on server and are often deployed in cloud environments, and they can be configured to on a virtual machine. Then further, load balancer can improve the performance and availability of a web application by distributing the traffic evenly across multiple servers, preventing overload, and ensuring that the user can access the application even if one server fails. They are commonly used in high traffic websites, e-commerce, and other web-based applications that require high availability and scalability. Okay. So now, like if you will see design, as of now, our design looks like this. So load balancer will here evenly distribute incoming traffic among the web servers that are defined in the load balancer set. So if you will see this diagram right, here the request is coming from the user to our website, and in between web servers, we will place our load balancer. And as we can see in the diagram, here user uses public IP to connect to load balancer directly. And with this setup, web servers are unreachable directly by the clients anymore. For better security, private IPs are used for communications between servers. Like load balancer uses private IPs to communicate data between internally between servers. And a private IP is an IP address reachable only between servers in the same network. However, it is unreachable over the internet. Like users cannot use this private IP directly to reach the web server. And the load balancer communicates with web servers through private IPs. And after a load balancer and a second web servers are added, and after this thing is added, right, we successfully solved no failover issue and improved the availability of WebTI, because now we have multiple servers in place and also load balancers in place. So if a particular server goes down, then load balancer can auto redirect that request to a different server. So in this way, we can avoid that failover scenario. So if server 1 goes offline, all traffic will be routed to server 2, and this prevents the website from going offline. And we will also add a new healthy web server to the server pool to balance the load. And like we can also add one more server later on to basically balance the load. And if the website traffic goes rapidly, and then like if the traffic goes up rapidly, then 2 servers are not enough to handle the traffic. Then the load balancer can handle this problem gracefully also. We only need to add more servers to the web server pool, and the load balancer will automatically start to send requests to them. So whenever that scenario happens, we can simply add more servers to our web server pool, and load balancer will auto handle that and will automatically send automatically send new requests or new request or divide request among these new servers too. So in this way, we can use balancer to scale up our system for more number of users. So that is pretty much on the load balancer part. Database replication. Database replication can be used in many database management systems with a master and slave relationship between the original master and the copy slaves. What I'm talking about, let's see this diagram. You see, till now we had a big chunk of big database, but since it's a big database, then there is a single point of failure, and like all the data is coming and it is needing netting for the single database, so it is increasing the load on this database. And its journals say in the computer science, like we follow that 80-20 rule. We say 20% time only data is written and 80% time data is read. So to basically so using a single database for that might cause problem, because we have to read so many times. But if we are reading so many times, then writing can cause a problem. So to avoid that, what we do is we divide our database into two databases, two categories of databases. One is the master database, and another is the slave database. And we generally use master database to write our data or update our data, and then slave database is generally used as a read database. So we generally have multiple nodes of slave database, and and one or two node of master data database based on our need also. Since we generally have more nodes of slave database because we have to read our data a lot. So in this way, we try to divide our big chunk of database into master and slave database. Slave database basically gets a copy of data from the master database, and it generally supports only read operations. All the data modifying commands like insert, delete, or update are sent to generally master database. And most applications since require high ratio of read or write, that's why master of the database system. That's why slave database in system are usually larger than the master database, right? So what is the advantage of this way of replicating data into two databases of master and slave? So the advantage is it helps us to get better performance as all writes happens in the master database, whereas all read happens in the slave database. This complete model improves the process and like basically helps us to run our queries in parallel. Like the read queries are running on different databases and the write queries are running on different database. So in this way, we can increase the performance of our system. Second advantage is it helps us to increase the reliability of system. So if one database server is destroyed by any natural disaster or any mishappening or so, then our data is still preserved in the other database nodes or so. It helps us to prevent the data loss as our data has been distributed across multiple locations or multiple nodes or so. The third advantage is it helps us to basically ensure high availability. So by allocating the data across different locations, our website remains in operation if the database is offline, as we can still access the data from any of the particular node. Like if there might be a case like a particular node is going down, but still there are other slave nodes or the master nodes to basically get the data. Okay, and then how we handle the scenario when any of the database goes offline. So suppose any slave database is going offline, then the read operations that have been directed to that particular slave database redirected to a different slave database, or it can be redirected to the master database for temporarily. And as soon as the issue is found, the new slave database will replace the old one. In case multiple slave databases are available, read operations are redirected to a healthy slave database, and new database server will replace the old one. Okay. Then now what happens if the master database goes down? So if then a slave database will be promoted to a new master, and all the database operations will be temporarily executed on the new master database now. So a slave data and a new slave database will replace the old one for data applications immediately but yeah, in actual production, in promoting a new master is more complicated as the data in slave database might not be up to date. So for getting that missing data needs to be updated by an in data recovery scripts also. Although some other applications like multi-master and circular application could help, but those steps are complicated and are beyond the scope of this course. But there are certain ways to handle this too. So yeah, you can see in this diagram, right? We have a web server and we have moving all the writing part to this master database, and then we have multiple read slave database which we can use to read data. Yeah, so that is pretty much on the database application part. We'll be discussing cache or cache. Cache is a temporary storage area that stores the result of an expensive response or frequently accessed data in memory so that subsequent requests are served more quickly. So it's basically a device which saves the data in memory so that it is easily accessed later on, or like not easily but quickly accessed later on also. So how it is helpful in our design, let's see. So as you can see the diagram, right, like previously we were sending the data directly to web server and reading the data directly. Previously web server was sending directly writing data directly to the database and was reading directly data from the database. So like every time we used to we are getting a request, our web server is making a call to database to read some data and then send that data to the UI. So reading the data from the database takes a bit time since they are generally a secondary storage also, and it takes time to read the data from there and display it on the UI. So it is not that much. It's fast when we go with this approach. So to ease down this and to improve this, we are introducing a layer between the web server and the database, and that layer we're calling it as a cache or cache tier. So the cache tier is a temporary data store layer, which is much faster than database. The benefits of having this layer is it helps to include the better system. It helps to better the system performance, ability to reduce the database. It reduces the database workload. It scales, and we can scale this cache tier independently too. So whenever we increase whenever a web server receives a request, it checks whether the data that has been requested for is available in cache or not. If it is available, it simply sends the data back to the client. If it is not, then it query the database further and then first store the data from the database to cache and then sends it back to client. This strategy is called read through cache, where we first read the data from database via cache and store it in cache and then just send it back to client. Other caching strategies are available depending on the data type, size, and access pattern. So, and one more thing, interacting with cache servers is simple because generally most of the cache servers provides API, and their API generally follow a similar structure. Like we can take the example of memcache, where where we can basically, for setting the data in cache, we can specify the key and the value of it, and for the expiration time, the time after which the data will expire or would be deleted from the cache. And then when we are fetching it, we can simply specify the key and we can get the value of that key from the cache. So in this way, we can use cache to set the data or get the data. Further, there are certain considerations we have to make while using a cache. So to decide when to use cache, we have to think whether the data is being read frequently by our frequently when our data has been read frequently but modified infrequently. Then it's a good use case of cache. Since cache data is stored in volatile memory or in memory, and cache server is not ideal for persistent data. So like if our data has been modified a lot, then saving it in cache is a bad idea because it is not we cannot persist the data in cache. It's in memory device, right? So we can say like cache is similar to our RAM in our computer, and the database is similar to the hard disk also or secondary storage in our system. So reading data from RAM is quite fast, but at the same time we cannot say was persist the data in RAM. And on the other hand, reading data from hard disk or secondary storage is a bit slow, but at the same time we can store or persist the data, huge amount of data for a very long time in these kind of storage also. And the second thing to consider is the expiration policy. So like it's a good practice to implement an expiration policy. So once a cache data is expired, it is removed from the cache. And when there is no expiration policy, the cache data will be stored in the memory for permanently, which is a bad idea because it can full up the cache. So it is good idea to have an expiration policy, expiration date for each data stored inside the cache. And but at the same time, it should not be the expiration time should not be very less, else the data will delete it too fast, and we have to frequently make a DB call to get the data back in cache or send the data back to client. Okay, then third consideration is the consistency. This means like we have to keep our data store and cache in sync. Like inconsistency can happen because data modifying operations on the data store and cache are not in a single transaction, are not generally happening in a single transaction. Now, the other things are like mitigation failures. So, single cache server presents a potential single point of failure. So, basically, we are saying if there is just a single cache, then there are high chances of of being of that cache being acting as a single point of failure. So, it's better to have multiple caches or have a mechanism where we can have different caches, so that if one fails, then other is there to support that. And the last consideration is the eviction policy. So, once the cache is full, any request to add items to the cache might cause existing items to be removed, right? Because the cache can only occupy a limited number of items. If it is full, then it has to remove some other item to make a place for a new item. But this thing is called as cache eviction. So we follow certain approaches for achieving that. Like one is that least recently used way, or LRU cache we say, where we basically first remove the least recently used outcomes, used item, and then add the new one. We call this is the most popular cache eviction policy. Then the other eviction policies are there, like there's LFU, it says least frequently used, or first in first out can be adopted. All these can be adopted to basically based on our use case, whichever we feel like it can be adopted. So yeah, that is pretty much on the cache part. Content Delivery Network, CDN. In this part, we will talk about Content Delivery Network, aka CDN. So a CDN is a geographically distributed network of servers that work together to deliver internet content such as images, videos, web pages, and other digital assets to users around the world. The main goal of CDN is to provide a faster and more reliable content delivery network by reducing the latency and improving the speed of delivery process. A CDN works by caching the content in multiple edge locations around the world so that the users can access the content from the nearby server instead of requesting it from a faraway server, which can lead to delays and slow loading times. This helps to reduce the load on the origin server and improve the user experience by delivering content faster. And CDNs are commonly used by large websites, streaming services, and e-commerce platforms to provide a better user experience, reduce server load, and ensure high availability and scalability of their service. If we will see our design so far, we can place CDN near to the geography of the user, and user can use it to get the static content more fast and in a more efficient way. Further, CDN also supports dynamic content caching, which is relatively a new concept, but that is beyond the scope of this. How CDN works is at a high level. When a user visits a website, a CDN server closest the user will deliver the static content, and if the user further the user from a CDN server, the slower the websites for them. For example, if the CDN server is in Mumbai and the user is in South Africa, then it will get then the user will get content slow. But if the user is in Delhi, the same country basically, or near same geographies, then he will get the content faster. That's why it's a good idea to have CDN closer to your user base, or have different CDNs for different geographies or so. So now there are certain considerations to make while choosing a CDN. First consideration is the cost. CDNs are generally earned by third-party providers, and we are charged for data transfers in and out of CDN. So caching infrequently used assets provides no significant back benefits. So we should consider more moving them out of the CDN. So whatever things are being used most frequently, those should be moved to CDN in a way. And then the second consideration is to setting up an appropriate expiry or date for the cache. For time-sensitive content, setting expiry date for the CDN or a cache is important because expiry time should neither be too long and neither be too short. If it is too long, then content might no longer if no longer be fresh, like it would be old static content. But if it's too less, then we have to frequently make a DP toll and frequently populate the CDN wide. And the third consideration is we should have a CDN fallback. So we should consider how a website copes up with the CDN failure. So if the temporary CDN is down, then if we hit that CDN link, we will get nothing in return. So to handle that, there should be a fallback mechanism which will detect that, and when that thing happens, then it would request the resources from the origin or from the original DB and get the data from there if the CDN is not working. And the fourth consideration is invalidating the files. Like remove a file from CDN before it expires by performing one of the following lookups. Like validate the CDN support object using API provided by CDN vendors, or use servers into several different versions of CDN object. Basically invalidate the files when they basically become older, or use versioning system to handle this. The goal of the CDN is to basically load your content, load the static content faster to the user. So yeah, that is pretty much on the CDN or content delivery network. Part we will be discussing stateless WebTI. So when we consider scaling the WebTI horizontally, we need to move our state, basically the user session data, out of the WebTI. A good practice to store session data in the persistent storage such as relational database or NoSQL. Each web server in the cluster can access the state data from the database. This is called stateless WebTI. Sounds a bit weird, right? But what we are saying is when we are basically horizontally scaling the application, then it's a good idea to move the whatever user data or session data is there to any kind of database. It could be a relational database or NoSQL database, but it's a good idea to move our state related information or user into the database instead of saying it is in the web server. Why? Because to understand this, let's go further and see what is stateful architecture. So if you see this diagram closely, right, for user A, we are saving his session data in our server 1, right? and for user B, we are saving for in server 2, and similarly for user C, we are saving the data in the server 3, right? So like whenever we will get a request from a user A, our load balancer has to redirect that request to server 1, for user B to server 2, and for user 3 to server 3. Okay. So the issue is that every request from the same client must be routed to the same server. That is the requirement or issue, you can say. This can be done. So one way to achieve this is it can be done with a sticky section in the sticky section in a load balancer. So like always, when the load balancer gets the same request, it will from the C user just redirect it to the same server. However, this adds a overhead, and adding or removing the servers will become much more difficult now with this approach, and it is also difficult to and challenging to handle the server failures. So suppose the server one fails, right? Now what to do, since the session data was there in the server one only for a user. So next time when the user request comes, we don't have any session data. So again, then we have to again ask user to basically create or again ask him to log in again so that we can create his session data and again. So basically, handling the failure scenario with this sticky session way becomes difficult because our session data, user data is residing in the server. So to solve this thing, we use stateless architecture. So in the stateless architecture, for each user request, we are saving the data in some shared storage or some DB, you can say. So whenever user gets a request from a user A, it will fetch its state from this shared storage, and then will get the session data of that particular user and will do whatever DB operation or whatever operation he wants to do with that particular user. But that state of the user will reside in the shared storage instead of the web server. So that is what this stateful architecture says. If I have to quote it, I can say in the stateless architecture, HTTP requests from the users can be sent to any web server which fetch the state data from the shared data store. State data is stored in a shared data store and kept out of a web server. Stateless systems is simpler, more robust, and scalable because it is simpler because we don't need to have that sticky section overhead and all, and it is more robust and it is easily scalable. In future, we can add a number of servers, and but still the user data will remain in our shared storage also. So this help us to scale things up very easily and help us to reduce the fault tolerance and basically increase the fault tolerance. That is pretty much on the stateless web tier stateful architecture, stateless architecture. Part, we would be discussing message queue. Message queue is a durable component stored in memory that supports asynchronous communication. Like here you see this thing in Tangle is a message queue. Message queue basically serves as a buffer which to distribute asynchronous request across different systems. The basic architecture of queue is quite simple. Like it has a input services called producer or producer, where basically a service can publish a message, and then there are consumers which basically subscribe to this queue. So whenever a new message is published to this queue by producer, these consumers are notified with the new message. This is the whole working of a message queue. And basically, consumers can perform action based on the message they got. Like if they want to update certain thing, or if they want to delete certain thing, or just to send a notify user, or email user, whatever they want to do, they can do it based on this the message they got. So what is the benefit of this is it helps us to achieve decoupling, and decoupling make the message queue a perfect architecture for building a scalable and a reliable application. So because with the help of this message queue, the producer can post a message to a queue even though when the consumer is unavailable to process it. Like a producer can produce a message, publish a message to a queue, and whenever the consumer becomes available, he will read the message from the queue and do whatever he wants to do with that. And why it is help us to scale the system because we can have n number of producers who can publish to message queue, and we can have n number of consumers queue, and the count of producers will not affect the performance of the number of consumers as well. Like those producers can simply keep on publishing message to a queue, and then consumers can read it whenever they want it. So we can easily scale any of them based on our requirement also. And we can we can do it like we can this thing can be used has lots of wide use case. Suppose we are building a video editing software or so, right? And we have done some certain trimming or basically improving the audio or sharpening. Like we have multiple multiple tasks, right? Then and each task can take certain time to complete, right? So we can our server can publish these different tasks to different publishing to the queue, and then different publishing jobs can pick up this task and work on them asynchronously. And in this way, basically producer and consumer can be skilled independently. Like we can have n number of consumers and number of jobs which are working on different features and all, and we can produce different effects on our use case also. So we can easily scale system. And when the size of queue becomes very large, we can add more workers or more consumers to it, or which can add. And when the size becomes low, we can similarly reduce the number of workers or consumers. So in this way, basically, message queue helps us to achieve this asynchronous communication across different systems or services. And in the below images, you can see the commonly and the most popularly used messaging queues. These are like Kafka. The open source ones are Kafka and the Evertime queue, and then there's a queue by Amazon called SQS, or simple queue service, we say. So yeah, that is pretty much on the message queue part.
Log, metrics, and automation.
So in this part, we will be discussing these. So when working with a small website that runs on few servers, we might not require logging metrics or automation. But as we go big, when we are serving a large business, investing in these tools is essential. And this makes sense too. So let's move further. Let's start one by one. So first of all, it's logging. So logging means monitoring error log of a system, and it is important because it helps to identify errors and problems in the system. And we can monitor error logs at per server level, or use tools to aggregate all of them at one centralized place, and then can have a search and view, can easily search and view at that particular place. This helps us to basically debug a bug or any production issue that happens, and basically have a log tail of whatever is happening on our production systems also. So we can have this logger in place, which is basically logging. We can have logger in place for all separate servers, or we can have a centralized logging system where we are taking where we are pulling the log of all the servers, and there we can see, search, and analyze and do whatever we want to or do with those logs. Then the second thing that comes is metrics. So metrics means collecting different types of metrics. Metrics means the stats, or basically some parameters of our system that we want to measure. Metrics means measuring something, right? The measure of something, right? So basically, it helps us to see or analyze our system on certain parameters. So like collecting different type of metrics help us to basically gain business insights and understand the health and the status of system. Some of the metrics that are useful to us are like on the host side. So we can say the CPU level metrics, the memory metrics, the disk input output metrics. And then on the aggregate level side, we can say, for example, the performance of the entire database, cache, tier, or CDN also. So these can be helpful on that side. And then there is a key business metrics that is on the number of daily active users, the retention rate, the revenue rate, and all these metrics are important from the business side. Okay. Then the third things that comes is the automation. The logging and monitoring part is almost is similar, is same. And so basically the fourth thing is the automation. So in the automation, we mean, right, when a system gets big and complex, we need to build or leverage an automation tool to improve the productivity. So then this continuous integration is a good practice in which each code is checked in its verified through automation, allowing them. So basically, we write unit tests, and we have different continuous integration frameworks in place like Jenkins and build tools, and unit test, automation test, integration test via these automation suites and all. This helps in continuous integration and basically helps us to check and verify the fitness of our system. And it also helps us to detect the problems early. Besides automating, we can automating the build, and we can also automate our build to via that, and the test suite will run via that, and we can also automate the deploy process. So in a nutshell, this having automation suite in place is very helpful, and it helps us to basically scale our system in a most efficient way, and able to handle or debug or basically solve problems in a most nice way, and helps us to improve our developer productivities too. So that's why it is good. It is must to have all these things when we are building a highly scalable system. So that is pretty much on the logging, metrics, and automation side. we would be discussing sharding. The sharding separates large database base into smaller, more easily manageable parts called shards. Basically, sharding means to basically separate out the big chunk of database into small parts. It is different from replica, because in replica, what we do is we make copy of databases in different nodes. But in sharding, we divide a huge chunk of data into small parts and basically host those small parts in different nodes or so. It's a way kind of slicing database into multiple parts and then fetching and retrieving data from these different parts. And these parts we call them as shard. And basically this each shard shares the or each shard or each part shares the same schema, though the actual data on each shard is unique to that particular shard only. So the schema is same in each shard, but the data is different because each shard is after all a part of the huge database, right? So the data would be different in each shard, but they will have the same schema since they are been sliced out from the same database. So as the diagram here shows, right? In the diagram we see we have a user database with us, right? Which we have divided into four shards. The user data is allocated on database server based on the IDs, right? We have different IDs. Anytime we try to access a data, a hash function is used, like we are using this hash function like this percentage or so, is used to find the corresponding shard. Like in the diagram, we are using this user ID %4 to basically find a particular shard ID or particular ID of the database that from where we can access the data. Is used to use as a hash function. If the result is equals to 0, then the shard 0 is used. Like if the output of this has shard function is 0, then we use 0, a 0 node as 0 shard. Shard 0 is used to store and fetch the data, and if the result equals to 1, then shard 1 is used to. Same logic applies to other shards, right? In this way, basically, we divide the huge database into multiple shards, and then we use hash function to find out like from which shard can retrieve a particular data. Like we pass that request data, pass the data required to pass the data, use this hash function to determine which shard can fetch us the particular data. So in this way, we use hash functions to basically access the data throughout different shards. The most important factor to consider when implementing a sharding strategy is a choice of sharding key. Like basically, we need to ensure a particular key on which basis we're dividing the shard. It could be ID in this example, or we have to decide on which base we have to divide which these shards, so that we can say like from range this to this keys would be there in this particular shard, and from range this to this would be there in the this particular shard. So in this way, based on the key, we can divide data across different shards. Sharding key consists of one or more columns that determine how data is distributed, right? And as in this case, the user ID is a sharding key. A sharding key allows us to retrieve and modify data effectively by routing database queries to the correct database. Like we're able to find out the correct database based on the sharding key, right? Like we know, okay, the sharding key is this, and this says the sharding key belongs to this shard. Key allows you to retrieve and modify data efficiently by routing database queries to the correct database. When choosing a sharding key, one of the most important criteria is to choose a key that can evenly distribute the data. Like sharding is a great technique to scale the database, but it has far from perfect solution. It comes with its own complexity also, because how to shard things, like, and like sometimes we also consider geography is in concern while sharding. Like we shard based on a column which tells us like this belongs to this country, so all the column, oh sorry, all the rows will belonging to that particular country will be shard to that particular database, and like based on the geography we try to shard things, right? So it comes with its own complexity also, and then there's a very famous problem called scalability problem. This is also called the hotspot key problem. In this, suppose we make excessive access to a specific shard, which may cause overload, which may cause server overload on that particular shard. And why we do it? Because suppose that shard belongs to celebrities. Like let's take an example of Instagram, right? Suppose we have in the particular shard we have the data of lots of famous celebrities like Justin Bieber, Will Smith, Tom Cruise, and all those data is being residing in that particular shard, right? And we're trying to fetch photos or data from that particular shard only. Then naturally the load on that particular shard, which is having the most of the celebrity data, will increase a lot. So this is a celebrity problem, and we have to find a way to mitigate this thing. For social applications, that shard will overwhelm. So like in this case, for this social networking scenario, this a particular shard can overwhelm. Solve this problem, we may need to allocate. So to solve this problem, we needed to allocate a shard for each celebrity, or each shard might even require for further participants. So like solve this, you might go with a way where there would be a single celebrity in a particular shard, or we can allocate separate shard popular celebrities or so. This way we can come up with the approach and try to shard in that way. Then another complexity would be the resharding data. Resharding data is needed when a single shard could not no longer hold more data to have to go to like a particular shard had become too large, then we have to there's a need to reshard it. Certain shards, then the second reason is certain shards might experience shard exhaustion faster than other due to uneven data distribution. When shard exhaustion happens, it requires updating the shard function and moving the data around, right? And consistent hashing, which will and there one such way is consistent hashing, which we will discuss later on in this series, but which is commonly used to solve this problem, right? Then the third complexity is the join and denormalization. So once a database has been sharded across multiple servers, it is hard to perform join operations across database shards. Like suppose we're writing a join query, then writing a join query across operations across different shards becomes a bit complex. A common workaround to denormalize the database so that the queries can be performed in a single table. Now, a common workaround is to basically denormalize our database in such a way so that the queries can be performed in a single table. Thus, we can say we shard our database to support rapidly increasing data traffic. At the same time, some of the non-relational functionalities are moved to a NoSQL data store to reduce the database load. Right. Sometimes we also try to move our shard data to a NoSQL database or some different kind of database to handle this thing in a better way. So yeah, that is pretty much on the sharding part. Back of the envelope estimation. So in this part, we will be discussing back of the envelope estimation. So what is back of the envelope estimation? It is a rough calculation or a quick estimation that is done without the use of extensive data or precise measurement. Basically, it's a kind of a rough calculation or rough estimation of the design or the infrastructure that we would be going to use when we will be building a certain application. Like it is used as a preliminary method to assess the feasibility of a project, like a feasibility of a software or a product or a API or a design in the computer science sense. It involves making reasonable assumption and using simple calculation to arrive at an approximate answer. Right? This makes sense. And the term back of the envelope comes from the idea that a quick calculation can be jotted down on the back of an envelope or a scrap paper. It is used in fields such as physics, engineering, economics, and business to evaluate the potential of an idea or a project. So similarly, we use it in engineering or computer science to basically evaluate whether a particular system design will be feasible or not. It's just a rough calculation where we basically roughly estimate things on the back of an envelope or back of a scrap paper, just on a paper or a whiteboard to predict like what would be the total size of the data and like what would be the CPU, like basically how much resources we have to allocate based on our design. So that we try to estimate that. So in a system design interview, we try to tell this about a particular design and say like this, if we are getting these number of users or this much of load, then we need this much of storage or this much of CPU performance or this much of services and all. So all this idea comes with the by doing this self calculation about our design also. Like it gives us a good sense of scalability basis to effectively carry out a back of envelope estimation, right? And few things to note here is high availability. So high availability states that systems should be highly available. By that I mean highly availability is the ability of system to be continuously operational, right, for a desirable long period of time. And high availability is measured as measured in percentage, and 100% means that the server has zero downtime. Like the website is 24/7 online, and there is zero downtime if it is high 100% available. And most services that we use are generally falls between 99 to 100%. Okay, like most services that we use lie between this range. And then the second thing that to notice the SLA. SLA is called service level agreement, which is a commonly used term by service providers. This is an agreement between us and the and our customers, and this agreement formally defines the level of uptime our service will deliver. Like this basically this is the agreement between our website and our customer, and this tells us like what is the it tells us what is the level of uptime of our service and what is the level of uptime our service will deliver. So generally the cloud providers that we see like Amazon, Google, and Microsoft set their SLA as 99.9% or above. PC they have such a high SLA. So if there's a downtime and all, then they might get that SLA incidents or severity 2 or severity 3. Like those who might have worked on production support, they might have know like how this SLA come in picture. So basically, in the nutshell, it says right, generally offer this high SLA, and to offer that high SLA, we have a back of envelope estimation multi right, so that our system should be designed in a way so that it should be able to handle that scale or that load. And as per the industry, the more the nines are there in that percentage, the better it is, right? So that is on this side. Now let's try to do a back of envelope estimates of a Twitter website, right? Right. And please note all these following numbers are only for the exercise purpose, and they are not the actual real numbers of Twitter also. So we can start by saying like we can assume like Twitter has 300 million monthly active users, right? And 50% of users use Twitter daily. Like total users are 300 million, but active users are 300 million, but 50% of them use Twitter daily, right? And user generally post two tweets per day on an average. Like two tweets are posted by a user on an average per day, right? And 10% of tweet contains media. Yeah, media by media means like images, files, videos, or so. And data is generally stored for 5 years for a tweet or by a Twitter also, right? And this is the assumption that we have. Now we have to do some back of envelope estimations using this data. So we can start by saying query per second, or QP as we call. We tell like what is the query per second data we are getting. So we can start with our daily active. We can start by calculating the daily active users. So we know we have 300 million active users, but 50% of them only use Twitter daily, right? That means what daily active users are 150 million, right? Then we are calculating the tweets QPS. Like so, here I'm saying query per second, right? Query per second. So 150 million out of 150 million users, they make two tweets daily as per our assumption, right? And so how many tweets they are making per second? We can divide it by the total number of seconds in a day, and then we will get 3,500 tweets per second. So query per second, right? That much data is coming to our system, and the peak QPS will happen when complete 100% users will use Twitter, right? So I can simply multiply my QPS with 2. Basically, 50% will become 100%. So it will be 7,000 QPS would be my peak QPS. Now, I have to estimate my data storage based on this, and I can say a particular tweet size is of 64 byte. Now, if I consider so like a tweet size and the tweet ID of a tweet of each particular tweet is of 64 bytes. The size of the text would 145 bytes, since we allow 140 characters in tweet. And then the media size, generally the files we upload, we are talking about average here, so would be 1 MB. So if I have to calculate the media storage that is required, so I can say there's 150 million people that are using my Twitter daily, and they're doing 2 tweets. But we know here there's also 10% of tweets contain 1 MB. So only 10% of total tweets are media. So I can simply multiply this with 10% and then into 1 MB. So I will be getting 30 TB per day would be the media storage size. And if I have to preserve the data for 5 years, then I would be multiplying this 30 TB into number of days in a year, 365 into 5 days. So I will be getting around 55 petabyte. So you see, this one in this way we can calculate based on our user data of the website. We can calculate the size of the data storage and the QPS, and then calculate the CPU performance and the node service. And all. We can do good estimation based on the user data we have, or based on the data we are expecting. Like this much would be our users and also in this way. So in this way, we do a back of envelope estimation of any system design problem also. Now few tips to consider here is always try to, since it's a estimation, right? So always try to do rounding and approximation, because it's difficult to complicate it's difficult to perform complicate math operations like during your interview. Like for example, multiplying 99.8887 like playing with decimals is quite difficult when you're doing manual calculation. So it's a good idea to approximate things as much as you can, and then just try to write down your assumptions whenever you're doing it. Like take pen and paper, whiteboard, and then try to label your units correctly. Like differentiate between like what you are writing. Is it 5 MB or it is 30 TB or PB? Like be particular about the units, and then the last thing is just be ready with the commonly asked back of envelope estimations. Like what is how much time storage, how much size the storage takes, what is the cache, what is the number of servers, and just have a basic idea of commonly asked back of envelope estimations also. So if you have this idea, you will be able to do your back of envelope estimates for any system design in a nice way also. So these are the approximations, and generally people ask them during the interview also. So that is pretty much on the back of envelope estimate part. Cap theorem. So in this part, we would be talking about cap theorem. So cap theorem, also known as Brewer's theorem, is a concept in distributed computing that states that it is impossible for a distributed system to simultaneously provide all of these three things. That is cap, basically consistency, availability, and partition tolerance. Let us first see the definition of each term. Like here, consistency stands for all clients see the same data at same time, no matter which node they connect to. Like whichever node client is connecting, they should get same data from all the nodes. Like all the nodes should have a consistent data. Second is availability. By availability, we mean any client which requests data gets a response, even if some of the nodes are down. Means any client should always get a response from the server, even though some of the nodes at the server are down. Still, the server should return a response to the client request. Then the third thing is partition tolerance. So by partition tolerance, we mean a partition tolerance. A partition indicates a communication break between two nodes. Okay. Then a partition tolerance means the system continues to operate despite network partition or network breaks. So basically, partition means a communication break between two nodes, and partition tolerance states that the system must still continue to operate despite there is a network break or a network partition between any two nodes or so. Systems should still function despite of any partition or any system break between any nodes. The overall system should still function. That is the thing the partition tolerance states. So cap theorem states that it is impossible for a distributed system to simultaneously provide more than two of these guarantees, like that is consistency, availability, and partition tolerance. Like a system can only be either consistent, like a distributed system here we are talking about, can only be either consistent and available, like a CA system, or it can be a AP system, highly available and which is available and partition tolerant, or it could be a CP system which is consistent and partition tolerant. If we talk each in detail, then the CP stands for consistency and partition tolerance system. AP is availability and partition tolerance system. CA is consistency and availability system. So if we start by CP, then CP supports CP supports consistency and partition tolerance on by sacrificing availability, and AP we support availability and partition tolerance by sacrificing consistency, and in CA we support consistency and availability by sacrificing partition tolerance. But since we know network failure is unavoidable, so a distributed system must tolerate network partition always. Thus, a CA system cannot exist in a real world application. Like we always need to ensure a partition tolerance. So a CA system existing in a real world is not actually possible. So this cap theorem has an important implications for the design and operation of a distributed system, as it highlights the trade-off that need to be made in order to ensure the system performance, reliability, and consistency. Different distributed systems prioritize different aspects of cap theorem depending on their specific use case and requirements. So basically, whenever we are designing a distributed system, we have to make trade-off between these three. Like we have to sacrifice any one of them to gain other two. That design call we have to make whenever we are designing a distributed system. So let's assume ideal situation. Let's assume an ideal world where basically network partition never occurs. Like the network break between two nodes never happens, right? Then suppose we have three nodes, N1, N2, and N3. And then when the data is written in N1, it is automatically applicated to the other two nodes, N2 and N3, as both consistency and availability are achieved. In the ideal situation we are talking about, where every three things is possible. But in the real world distributed system, partition cannot be avoided. Like partition must happen. Like the break might happen. Break will bound to happen sometime or then. And when a partition occurs, we must choose between consistency and availability. Whenever partition occurs, then we have a choice to make: either go for consistency or go for availability. So let's suppose out of these three servers that we have, N1, N2, and N3, N3 goes down, and it can no longer communicate to N1 and N2. Okay, and now if client side data to N1 or N2, then data cannot be propagated to N3 because N3 is down. So if data is to be written in N3, but not data is to be written to N3, but not propagated to N1 and N2, and yet N1 and N2 would have and the converse we are saying also will happen. Like if we have written something on N3 and it has not been propagated to N1 and N2, and N3 has got down, so it will not be, since N3 is down, so it will not be propagated to other two. So that can also happen. And so if we choose, so in this scenario, if we make a choice to have a consistent system, if we choose consistency over availability, basically a CP system, then we must block all the write operations to N1 and N2 to avoid data inconsistency among these three servers, which makes the system unavailable. Okay, so like since N3 is down, so now to maintain ensure consistency throughout all our nodes, we should stop writing of data on other two nodes, so that if nothing is written, then basically all the nodes will have the same data, right? So we will not sacrifice consistency in this way by stopping any write. But if we are stopping any write, then basically client cannot write anything to the server. That means this writing thing is unavailable to a server. So basically, we in a way we have sacrificed availability for the sacrificed the ability to write on the system to the client. So we have sacrificed availability here just to gain the consistency. So yeah, in this way we had built a CP system by sacrificing availability on our end. So if we're talking about a banking systems which usually have extremely high consistent requirements. For example, it is crucial for a bank system to display the most up-to-date balance info of a person. So like if something is been debited or added, the bank should always show the most immediate or most recent update of the balance of system. Like the banking system should be highly consistent. That is a goal while you are building a banking system. If inconsistency occurs due to the network partition in that banking system, then the bank system must return an error before inconsistency is evolved. Till the time if suppose any partition happens on the banking system, then the banking system should become unavailable or should return error till the time the consistency has been resolved. In this way, the banking systems are always CP systems. They become unavailable when the consistency suffers due to some partition also. However, if we choose availability over consistency, like we are choosing AP system, then the system keeps accepting reads even though it might return a stale data. Like suppose node 3 has gone down and we have written some new data to node 3, but now node 3 has gone down, right? Now if we are fetching the same data from the other two available nodes that are N1 and N2, we will get the data, like system would be available, but the system would have the old data. So we are sacrificing consistency for favoring the availability. And our N1 and N2 server will also keep accepting writes. The data will be synced to N3 when the network partition is resolved. So the N3 will be now sitting in the older data, and N1 and N2 will keep on getting the new data, and then the overall consistency of the system is lost, but we are maintaining the availability here. So choosing the right cap theorem is an important choice we have to make while we are building a distributed system. And we can all discuss this with our interview, and based on the functional requirements and the non-functional functional requirement, we can basically decide on which type of system we want to go, whether it is a CP system or it is an AP system. Based on this cap theorem thing, we can decide which trade-off or which choice we have to make while building our system design. Okay, so yeah, that is pretty much on the cap theorem. Thank you. So last in this section, I can say like scaling a system is an iterative process. And iterating on what we have learned in this section, we can say more fine tuning and strategies are needed to scale beyond millions of users or so. Like there's a need for some strategies and some methods to scale beyond million users. For example, we need to optimize our system and decouple the system to even smaller services if we want to scale it large. All the techniques that we have learned so far in this section should provide us a good foundation to tackle new challenges and solve these system design problems. To conclude this thing, I can summarize this thing in certain points, and they are as follows: like try to maintain statelessness in the web tier. Try to build a stateless systems. Like try to move your session in the shared storage instead of web servers, as we saw previously in the particular part. Then try to incorporate redundancy at each tier. Don't never try to have a single point of failure. Try to have database applications, or try to have database applicas, or try to have shards, or never try to have a single point of failure. Try to have multiple nodes of cache, queues, CDNs, or so. Then third point is try to utilize caching to the fullest extent possible. Like whatever things is being required again and again, try to cache that in that cache system also. Try to move those things there so that every time so that you can get fast response also. And then host static resources on a content delivery network, CDN. That makes sense, so that you can get them faster, and those are geographically near to you, so you can easily get them. Then the fifth point is try to implement data tier scaling through sharding that we saw previously, and then divide tiers into distinct services. Try to break down your big chunk of monolithic services into small services. If you are building a very large or scalable system, then going with this way is better, like dividing the big monolithic chunk into small microservices, and then those microservices can be scaled based on the load they are getting also. So in this way, you can design your system. And last is the monitor the system and utilize automation tools for optimal performance, like monitor your system through different logging services, or having a centralized log and so, and then use certain automation tools and unit tests to properly test your system, and to ensure that it should provide that optimal performance also. So yeah, so that is pretty much on the summarizing part of this.